Okay, kids, we're back here, and as we're kind of going through this chapter pretty quickly, just trying to give you the highlights so at least you have some understanding of this. Like I said, it's a pretty specialized topic, not critical to someone's career as an engineer or a doctor or a nurse or something like that. But nevertheless, I find it very interesting. So what we're going to talk about now, and I hope you watch the video. They're older videos, but they still do a good job. So relativity, mass and energy, first concept, which was hinted at in the previous section of the textbook. The idea of rest mass. Okay, rest mass, M. So this is the mass of an object as measured by an observer at rest with respect to the mass. So there's no relative motion between them. So here's my textbook. I'm going to measure its mass, put it on a scale, and that's it. Okay. Now, relativistic mass is the mass measured by an observer with a relative velocity v with respect to the mass. So there's the equation for the relativistic mass. So you've seen this in this root quite a few times. A lot of textbooks call this root gamma, just so you don't have to write it all the time. All right, so that's the first concept. Now, the other thing Einstein really brought forward is that he proved, and it's been proved many times now, it's how we get energy from the sun through fusion, nuclear fusion, as massive hydrogen is converted into helium, and some mass is lost when that conversion happens, and that mass that is lost is turned into energy, and that's the energy we get from the sun. So rest mass is a form of energy. So what Einstein said is you can take rest mass and you can convert it into light. You can convert it into photons, which is a form of energy. And what's really cool is it can go the other way around. If the conditions are right, you can get photons being converted into mass. So it's rest mass and light photons. They're like two sides of the same coin, depending on the conditions that are present. You can get conversion one way or the other. And then here's the very famous equation. I didn't want you to leave high school with at least one note with this in it. The E equals mc squared, right? That if you have the rest mass of an object, you multiply it by the speed of light squared, that's how much energy will be produced. Or if you've got some photons, some energy of light, and you divide it by the speed of light squared, that's how many kilograms of mass you'll produce. You can actually produce mass, and the other way around. Next concept Einstein came up with was what is the total energy of an object then, right? And here's the equation right here. So once again, it's our root in right there, 1 minus v squared over c squared. This comes up a lot, as I've mentioned many times. And you would calculate the rest mass, mc squared, but then you'd have to have the root in the denominator. Now, for many moving subatomic particles, like an electron or many other exotic particles, you can actually calculate the total energy, but usually the common unit is not the joule. The unit that they would use is the electron volt, and 1 electron volt is 1.6 times 10 to the negative 19 joules. And depending on how much energy in there, you can have kilo electron volts, keV. You can have mega electron volts, MeV. So all of those prefixes that we learned, oh, when we just got together back in grade 11, seems like yesterday, you can have this unit scaled like just like any other unit. And with the idea of total energy and rest energy, we now have a new definition for the kinetic energy of an object. So this is the kinetic energy of an object, the relativistic equation. You're used to kinetic energy being half mass times the speed squared. And that's fine for Newtonian classical mechanics when the speeds are very, very low. But really when the speeds start to approach the speed of light, this is the equation right down here you need for kinetic energy. So I hope you watch the video. Read the textbook. There's some sample problems there. The sample problems and the practice problems basically just come down to plug and play. You all know how to read stuff out of a textbook. So there you have it for today. Like I said, kids, just trying to give you a little taste of it. Most of the, well, all of the critical stuff I made sure that we covered in greater depth. Bye bye. Have a great day.